If you've ever taken a course on differential equations, you've definitely met the Wronskian. It's presented as this foolproof test for linear independence. But, there's a huge catch, a really critical exception to the rule that a lot of people miss. So today, we're going to uncover that big secret about the Wronskian that you absolutely need to know.
So, this is the big question we're tackling today. We're all taught this simple rule of thumb. If the Wronskian is 0, the functions are linearly dependent. But, as we're about to see, that's not always true. It all comes down to the context, and understanding that context is the key to not getting tripped up.
All right, before we get to the juicy part, let's do a super quick review of the fundamentals, just to make sure we're all on the same page.
So, what does linearly dependent even mean? Well, in simple terms, it means one function is just a scaled up or scaled down version of the other. Think of sine of t and 3 times sine of t. They aren't fundamentally different, right? One doesn't bring any new information to the table. That's linear dependence.
And this is where the Wronskian comes in. It's our go-to mathematical tool for checking this relationship. It's basically a special kind of determinant that we build from the functions and their derivatives. And whether that determinant turns out to be 0 or not tells us a story about their independence.
Okay, basics are covered. Now for the main event, the nuance, the twist, the specific little detail about the Wronskian that so often gets overlooked.
This is the rule they teach you on day 1, right? If the Wronskian isn't 0, the functions are independent. If the Wronskian is 0, they're dependent. Clean, simple, easy to remember.
Yeah, almost. That beautiful, simple rule comes with a massive asterisk attached.
And here it is. This is the crucial distinction. That perfect if and only if relationship, where w equals 0 means they must be dependent, that only works if you already know your functions are solutions to the same linear second-order ODE. If you're just dealing with some random functions you picked out of a hat, well, then the rule is only a one-way street. A non-zero W-skian still guarantees they're independent, but a W-skian of 0, it actually tells you nothing for sure.
I know, that might sound a little heady, so let's make it real. We're going to look at a classic counterexample that just brilliantly shows off this hidden catch.
Okay, so let's check out these two functions, t squared and t times the absolute value of t. That little absolute value function is the key to this whole thing. Okay, let's break this down. When t is positive, the absolute value does nothing. So our functions are just t squared and t squared. Obviously dependent, so the Wronskian is 0. Now, when t is negative, the absolute value of t is negative t. So our functions are t squared and negative t squared. Again, one is just a multiple of the other, so their Wronskian is also 0. So the Wronskian is 0 times everywhere. But, and this is the kicker, you can't find a single constant k that makes t times absolute value of t equal to k times t squared for all t. They are actually linearly independent. This proves it. A 0 Wronskian doesn't always mean dependence.
So now that we know the secret rule, let's actually put it to work and see how we can use the Wronskian correctly with a couple of practical examples.
First up, let's test a set of 3 pretty standard polynomial functions, t, t squared, and t cubed. This means we're going to have to calculate a 3×3 determinant.
So here's our setup. The first row is just the functions themselves. The second row is their first derivatives. And the third row, you guessed it, their second derivatives. Now all we have to do is find the determinant of this matrix.
So we'll use cofactor expansion along that first column since it has a 0 in it, which makes life a little easier. We get t times its little determinant minus 1 times its determinant. And when you work through the algebra, it simplifies all the way down to 2t cubed. Since this is not 0, as long as t isn't 0, we can say with 100% confidence that these functions are linearly independent. This is that one-way rule in action.
Okay, for our second example, let's get a little creative. We're going to flip the script. Instead of testing functions, what if we're given 2 solutions, like e to the t and e to the 2t, and we want to find the differential equation they belong to?
So here's the strategy. We assume they solve a standard equation like the one you see here. We just calculate the derivatives for both solutions, plug each one into the general equation, and what we end up with is a system of 2 equations with 2 unknowns, p and q. We solve that simple system, and we get p equals -3 and q equals 2. And just like that, we've reverse engineered the original differential equation. Pretty cool, right?
And finally, I want to share a pro tip with you. This is a strategy that can save you a ton of work, because sometimes the smartest move is to just not do the calculus.
Take a look at these two functions.
Now, your first instinct is probably to start taking derivatives, right? Your brain is gearing up for the chain rule, you're picturing this messy Wronskian calculation.
But hold on. Stop right there. Before you jump into a complicated calculation, you should always ask yourself, can I simplify these things first? Is there some algebraic or trig identity I can use? It's often the fastest way to the answer.
So let's see what happens. We all remember the double angle identity for cosine, right? Let's just substitute that into our second function. We get 1 minus the quantity 1 minus 2 sine squared t. Well, look at that. The 1's cancel out, the negatives make a positive, and we're left with y2 equals 2 sine squared t. And remember, our first function was just sine squared t.
We just proved that y2 is just a constant multiple of y1. It's exactly 2 times y1. So by the very definition, they are linearly dependent. We got our answer without calculating a single derivative, and we avoided the whole Wronskian mess completely. Always look for the shortcut.
Look, the Wronskian is an amazing tool, but like any tool, you gotta know its limits and when its rules actually apply. It really makes you think, doesn't it? What other math rules that we take for granted might have their own subtle, hidden catches just waiting for us to find them?